All right. Hello, my name is Wesley Bouchard, and for my Lab 5/final project for MEGN441 Intro to Robotics, I built MOSCAP, which is a simulator for Arduino-based robots. So the guiding problem statement here is that essentially a lot of things in robotics just are not very accessible, or there are just a lot of barriers to entry for hobbyists and learners and people who don't do this stuff professionally, right? So robotics hardware can be really expensive, of course, and that's not even what you're thinking in terms of high performance actuators and whatnot. Even the little Arduino robots that we use in lab are like $150 on Amazon, which is something that can really be out of reach for a lot of hobbyists or students, especially in high school. And then on top of that, a lot of the software-based educational tools and simulators and things provide their own barriers to entry. This can come in the form of like super complicated installation and usage patterns. So this is especially prevalent with Gazebo and ROS. You have to really be running Linux, and you have to understand how that works. You have to understand how to use a package manager. You have to do all of this setup, and what comes along with that is you also have to have just like a large amount of prerequisite knowledge for how to use them. You need to know C++. You need to already know what you want to do and then learn the tool to be able to do it. It's really difficult to learn the tool and to learn the concepts and content at the same time, and that's really challenging. And so really the question arises, how might one create an educational robotics platform that is simple to install and use, and that can leverage users' existing knowledge to provide educational opportunities without such barriers to entry? And so that's where my project MOSCAP comes in. It provides a simulation platform for Arduino-based robots, like the cars that we use in lab throughout this semester. And this is super important because for a lot of high school students, and especially for a lot of mechanical engineering students who are trying to learn some of these more controls and software concepts that are integral to robotics, the lens of Arduino code, it already makes sense to them, whether they've taken the spine of mechanical engineering tracks, MEGN 300, and so on, or whether they're a high school student and they had a STEM class one semester, or they went to a summer camp where they learned how to use Arduino, right? It's a very accessible platform that a lot of students already know, and so that takes out a chunk of having to both learn a new tool and learn content, because they don't have to learn the tool, which is Arduino. And the goal with MOSCAP is that they really don't have to learn the tool, and we're just trying to remove that kind of friction, right? So we're going to get into some of the different functionality here. So the first part is the physics simulation, and this part of the simulator is designed to be very extensible, right? So we have a base class that can be specialized into any dimension of state and input vector. So we could do wheeled mobile robots with 6 states. X, Y, theta, and then VX, VY, and omega for your states, or you could have like a 2R manipulator that had 4 states, the positions of each joint and then the velocities of each joint. And then implementers of this simulator class need to only write 2 functions. They need to write a function that updates the hardware with the current state, and one that translates the outputs from the hardware to inputs to the plant. So an example here, the one that I implemented for this kind of proof of concept or for this semester is a Mecanum wheeled mobile robot simulator, like the ones that we used, very similar to the chassis that we used in lab this semester, right? So like I mentioned, the state vector has 6 components and the input vector has 4, which is the torque that each motor is producing, and which is the torque that each motor is producing. So the hardware update step uses the changes in state to calculate encoder offsets. So you use some forward kinematics from the plant to determine how much each wheel has turned between physics updates, and then you can update the simulated encoder with that value so that the user's code can read that and read counts from it and run their control loops with it, and then set plant inputs, gets the torque that is currently being produced by each motor, runs it through the inverse, runs it back through the kinematics, and uses that as inputs to the plant for each physics update step, which in this case happens at 1 kilohertz or 1,000 times per second. And so now we kind of move into the Arduino interface. And right, the goal here is to be very minimally intrusive into the user's code, which is their Arduino sketch. So the user just has to implement one function, which is siminit, and then the rest of their code, the goal is that it stays very much the same. Right, so over here is an example of that function where we create a simulated mechanical robot. We register a motor to it on pin 28, and then we also create a button that's attached to that robot called test on pin 1. Now, of course, motors actually use 3 pins, but because of the way the simulator works, we only need one identifying pin to identify the motor. And in the user's code, the provided motor object can still take 3 pins. So that's, sort of in service of that minimally intrusive nature, right? And so the idea here, and you can see this here, is that the simulator, or the robot in this case, owns the simulated hardware, and it hands out handles to the Arduino runtime that the user's code can access and use to get and set values for different sensors or actuators or something like that. Now, something to note here is that more complex pieces of hardware like motors and encoders do need their own wrapper functions. So you couldn't implement a motor on the user code side with just digital reads and writes. It just doesn't work that way. But similar to how you can download an encoder library for Arduinos, it's a very similar concept here, where and this is okay because the focus is really on the robotics concepts and not necessarily the nitty-gritty of when do you have to set each pin to what to make the motor turn a specific way, right? And so next, we're going to look at rendering. So obviously the simulator is a graphical application. You need to be able to visualize what the robot is actually doing in the world. And then there's also a bunch of telemetry data that you can look at and that you can write. And what's great about this is anything can render to the screen or write telemetry data. It's not just the simulator code, the user code. The Arduino sketch can also do this. And the core idea here is that there's 3 kind of classes that objects can extend. They can be renderable, they can provide telemetry, or they can accept input. The input acceptor is a bit of a weird one. It's mainly just for the buttons right now, but you could do a bunch of other stuff with it, which would be really cool. And then for rendering, you can also directly register a function to be called every frame. This is great for drawing static shapes like the path on the ground in tape for lab 3, for example, where that doesn't move. And that's not necessarily associated with a piece of hardware or a piece of the simulator. It's just something you want on the screen. And the core concept here is layers or priority, right? So this helps us determine where to draw or write each piece of telemetry. By default, the robot or the core simulator that everything is running from renders to layer 0. So if you wanted to lay something underneath that, seeing this example here, that the white box is the robot, the red box is a box that the time of flight sensor can see, and then this is the green path like we saw in lab 3. So the green path is rendering to layer -2, the box is rendering to layer -1, and the robot is rendering to layer 0, which is on top of all that. But if you wanted to overlay some information onto the render window, you could render to a positive layer, and that would draw on top of the robot. And it's a similar idea with telemetry, where the robot writes to priority 0. And so see these buttons here have a priority of -1 because they are written above the robot position, and then everything afterwards is written afterwards. And so finally, we have our installation and usability component. Like I mentioned before, one of the goals of MOSCAP is for it to be incredibly easy to install and use. And so how I accomplish this is I packaged the simulator into a VS Code extension that's available on the extension marketplace. So this is a one-click install, and the extension handles toolchain and configuration and all of that nitty-gritty stuff automatically. And what's great about this is we can compile the entire simulator to WebAssembly so that it can run in a browser. And so we don't need to deal with any finicky graphics backends. And then the user interacts with this through some commands that the extension exposes into the Visual Studio Code environment. So you can see here we have start simulator and initialize environment. So the idea is that you just open a sketch, you hit Command Shift P or Control Shift P, and you hit start simulator, and the extension takes it from there and does everything you need to. And then finally, we have just some connections to the course content this semester. Obviously, this isn't as closely connected as like a physical hardware project might be, but I did make heavy use of like the DC motor physics lessons to implement the simulated motors. Our kinematics discussions were very helpful. And then transformation matrices are all over the simulator. And then there are obviously some ancillary connections as well with general robotic simulation tooling like Gazebo, and then other tooling because this is in essence a tool. And so there are definitely some connections there as well. And then looking to the future, one thing that I'd really like to do is make this extension work for VS Code on the web. Right now, it has to open the extension in a dedicated browser window, but that doesn't have to be the case. It can open in a window inside VS Code itself. So this would make it possible to open the VS Code web app in a browser and run everything self-contained inside that, which would be great, especially for high school students whose schools don't let them install applications locally, and so they have to access it through the web. That would just really improve access to this, and that'd be great. Another factor here is toolchain size. So for the WebAssembly compiler and all of the associated tooling, the extension has to pull about 3 gigabytes of toolchain onto the user's computer to make this all work. And that's just a lot of space, and a lot of it I don't think is necessary. A C++ compiler can only get so small, but I think there's definitely room for improvement there, because burdening a user and taking up 3 gigabytes of their space is just not something that really fits with the ethos of this whole project. So that's something that I would definitely want to address in the future. And then just generally the functionality, right now sensors and motors operate ideally, and it would be awesome to be able to incorporate like noise into sensor readings and stuff, because I think it would provide a lot of educational value in terms of how do you actually interact with hardware when you're writing these kinds of systems. And so something like that would be really great. And of course, adding support for more robots and just more general use cases. And this kind of leads into the last point, which is documentation, demos, and challenges, where you just really want to provide as much information as possible to the users of this extension, so that people who are trying to learn can use it easily, and that maybe educators, if they wanted to incorporate it into their education environments or curricula, could do that with minimal friction as well. And so that's kind of where I would like to take this in the future, and what could be done about that. And so now we're just going to do a quick demo over here. That's the recording software. So this is an example of an Arduino sketch. It should look very familiar. Right, we have a bunch of defines for different pins for motors and encoders and whatnot, and then we create motors and encoders here. We have 3 different buttons that we read from. The forward button will run the motors forward, and the left button will turn the robot left and right and whatnot. This is all pretty simple stuff. And so that's what a user's sketch might look like. And then this is a fairly complicated sim.h. But it gets the point across. We have some rendering stuff here, but you can see we create the robot, we set an initial position for it, we create a configuration for the time of flight sensor and add an obstacle that it can detect. We register that sensor with the robot. We do similar things for the motors and encoders, and then we register the buttons with the runtime. And then this is an example of how free functions can be added to the renderer. So this is the function that draws the lab3 path onto the screen. And up here you can see we register a draw function on layer -2, and the function is the draw path function, which is defined down here. So that will draw to the screen. And then startup is super easy. We can just say Command Shift P, MOSCAP start simulator. You can see it'll pop up a little thing that says compiling sketch, and when that's done, it'll open in the browser, and you can see these the buttons that we declared in sim.h have been wired to the telemetry panel, so we can press them here, and the user code can read their values, and it sets the motors accordingly. And see, this is the line that gets drawn by that draw path function, and here's the obstacle that we added for the time of flight sensor. And you can see that right now, time of flight sensor is reading about 34 centimeters, and if we just turn some more, now it's reading about 2.3 meters over to the other side of the box that the simulator exists inside of. And so this is where the simulator is right now. This is the functionality that I've built, and I'm super happy with it. So thank you so much for taking the time to watch this presentation. I hope that you think this is as cool as I do. And if you would like, you can install MOSCAP on your computer right now if you have VS Code. And so it'd be awesome to just see somebody else give it a try and see what their experience is like. So yeah, thanks so much.